Well, let's start looking at these things called exponents. Like I've tried to make clear before, the mathematicians do not invent these things. They sort of discover them. It's like algebra and all the math. It's always been there and we just figure it out. Now, there are some notations that we've invented. And one thing that I'd like to say is that in some parts of the world, a comma is used where we in the United States use a decimal point, and a decimal point is used where there's a comma. And so that would change everything as far as how your arithmetic works. And we've had students that have come to our school from other places and taken a basic math test and failed it because they got these two symbols backwards. And as soon as I said, well, the decimal point is for the fractional part and the comma is for every 1,000, they go, oh, and then they go back and get a perfectly good score on their test that was given by the state. That was a number of years ago before the recent bash of tests. But we want to talk about exponents, and the mathematicians did invent an exponent, but then how they act was a thing of discovery. If x is standing for an unknown, and you add another one of those unknowns to it, and add another one of those unknowns to it. Say I've got a certain amount of this, and I get another same amount, and the same amount, and the same amount. This gets kind of awkward. And so early on, mathematicians said, if you have one of those, and one of those, and one of those, and one of those, why don't we say that we take these numbers in front, and if there's not one, it's an understood one, and this would be 4x. Easy enough. The use of a coefficient with variables. Now, all these x's have an understood 1 exponent. And you can see when you add things to the first power, you get something to the first power. But then you have adding and then subtracting, which is just adding in reverse. And then the next thing, if you remember, that you learned was, I think I just better clear all that. The next thing you learned was to multiply. And if you take these mystery numbers and say, I have x, and I want to multiply it by another x, and I want to multiply that by another x, well, x times x times x times x, you can't use that to say that that's 3x, because 3x was x plus x plus x, and you can't have the same notation mean two different things. So somebody suggested that they put numbers up in the air, and that we could simplify this or use it as a shortcut to say x cubed. So x cubed really is shorthand for x times x times x. Simple enough. Well, then what happens if you start to multiply things that have exponents on them? Let's see what happens. I didn't make a very good square there. Let's clear that again. If you had x squared times an x cubed, we go back to what the exponent means. This is the same as x times x, and this is the same as x times x times x, and so that would be 1, 2, 3, 4, 5 of them. And somebody said, well, why would we have to write down what this means and write down what this means and then reinterpret it if we just notice that when we multiply, we add exponents. Now, if there's another number like coefficients on these, like 3x squared times 2x to the 5th, well, multiplication is associative, so you could rearrange it. So this could really be 3 times 2 times x squared times x to the 5th. And, of course, 3 times 2 is still 6. So we can come to the understanding that if we have coefficients and we had multiplying, the coefficients would multiply as they always have, and that the exponents would add. I hope you understood that. Multiply. Coefficients work like they always have for multiplication. but the exponents add. I'm going to clear this, but I'm going to have to rewrite that rule, that when we multiply, we add exponents. Well, what if we divided then? What if we had x to the 5th divided by x squared, and this would mean 1, 2, 3, 4, 5 of these, and this would mean 2 of these. Then this one would be divide numerator and denominator by x. We get 1, and we end up with x cubed. And some astute person said, why should we mess with all of this? We can see what happens. When you multiply, you add exponents, and if we have x to the 5th divided by x squared, you just subtract the exponents. So if we divide, we subtract the exponents. Well, what if you had x squared divided by x to the 5th? What would that mean? X times x, and 1, 2, 3, 4, 5. This x would cancel out this x, leaving a 1 behind. This would cancel this out, leaving a 1 behind, and we would end up with 1 over x cubed. Oh, so if there's more x's in the denominator, they could end up in the denominator. Or, if you follow the rule, you could subtract the exponents. 2 minus 5 would be x to the negative 3rd. So, all of a sudden, the guys have invented negative exponents. What does x to the negative 3rd mean? It means 1 over x to the positive 3rd. So we had the invention of the negative exponent. Nothing to be afraid of. Let's clear that. And so I like to say if we had 15x, no wonder I've got this tablet crooked, no wonder I can't write, x to the 5th, y to the 6th, z over 25, x squared, y, z to the 5th. We could just attack 15 and 25, both divided by 5. So we could divide this by 5 and get 3. This divided by 5 is 5. And then the x's would have their fun. If you have x to the 5th in the numerator and x squared down below, subtract those. The numerator wins, so we have x to the 3rd. Here the numerator wins again. We have y to the 6th and y to the understood 1, so that'd be y to the 5th. That's taking care of the y's. Oh, but the z's have more in the denominator, so this z to the 1, we deal with this. It would cancel with one of the z's down here, so it would be, this would cancel out, and we'd have z to the 4th. So that original problem would be 3x cubed y to the 5th over 5z to the 4th. Not too hard. I hope you get the idea of dividing, subtracting exponents. But remember to treat the coefficients like they've always been treated. 15 divided by 25 is just a fraction of what I call kindergarten numbers. Their rules did not change. It's the exponent rules that have funny things going on. I'm going to clear this again. Let's talk about raising to a power. What if we had x squared cubed, and we raise a power to a power? This cubed means that this thing is repeated 3 times, so it really means x squared times x squared times x squared, and when you multiply you add, so the answer to that problem would be x to the 6th. Let's see if we can extrapolate a rule here. Raise a power to a power, multiply the powers. Raise something that has a power on it to a power, you multiply the powers. Now, this is a little bit of a variation if we had a number in here, like say we had 2x to the 3rd to the 3rd. Then the 2 would get raised to the 3rd, which would mean 2 times 2 times 2, which would be 8. The kindergarten numbers would just be repeated 3 times. But raise a power to a power, this would be 8x to the 9th. I hope you will use my 2 programs, Laws of Exponents and Introduction to Exponents, to practice this and make sure that you get the right feedback. And maybe use some of the essential algebra worksheets to make sure that you are really good at multiplying and dividing and raising to powers with exponents. Thanks. Bye. Here we are going to look at the courses menu, and I'm going to pull up a whiteboard so that I can use it in case I need to make some notes. I'm going to push C for clear, and hopefully I can keep that down here, and I'm going to end this. And now we're going to look at algebra x squared, x cubed, and we're going to start looking at the rules of exponents. I have 2 major programs on exponents, and this introduction to exponents I really wrote for like middle school and for remedial algebra, but then the Algebra 1 teacher started to use it. The thing I wrote for Algebra 1 was this Laws of Exponents, which is what I think is the stronger of the 2 programs. But let's use this Introduction to Exponents as an introduction to exponents. It's kind of simple. I think I wrote it in a couple of nights because they wanted these kinds of problems. And they're just asking you to do the kinds of problems that are in all algebra books. So here the 2 parentheses are next to each other, and I probably should use the marker instead of the whiteboard, but let's see. We want to multiply those. See, the 2 parentheses are next to each other. It's implied multiplication. So we're really multiplying 4x squared. And only the x is squared, the 4 is not squared, or the 4 would be in the parentheses if it was under the control of that x. And 5x squared. This is not a very satisfactory problem because you could break the rules and sort of by accident get the right answer. The coefficient I usually refer to at the beginning of Algebra 1 is a kindergarten number. You learned how to multiply and add them when you were in elementary school. We did not change the rules on those. 4 times 5 is still 20. The kindergarten numbers are the ones that are sitting on the line. These guys up in the air are the exponents. Things with the same base, these are being multiplied, x squared times x squared. And when you multiply things with the same base, you add the exponents. Now it looks like we're multiplying, but we're really not. It's 2 plus 2 is 4. So this is 20x to the 4th. So we can put the answer in here. 20x to the 4th. And check, and we win. Now here is a problem that sort of helps you understand what the exponents mean. What does it mean? This is what the mathematicians really invented, was the exponent. If you said a mystery number x times that same mystery number times another mystery number times that's another mystery number times that other one times that other one. Well, look, it gets ridiculous. The mathematicians said there's got to be a better way, so they invented the exponent. And you wouldn't put it on the line like the kindergarten numbers because that would mean x plus x. See, here's a 1 plus a 1. That would be 2x. But when they're times each other, something else is going on. So they said if you have 2 x's times each other, we could write that as x squared. And if we have 4 y's multiplied together, that would be y to the 1 plus 1 plus 1 plus 1 to the 4th power. So this is x to the 2nd, y to the 4th. Hope you got that. Check, we win. Here's the same sort of problem before, but now this time we don't have an x squared. Let's see if we can do this one without using the marker. The kindergarten numbers, 5 times 2 is still 10. X cubed times x squared is x. When you multiply, you add the exponents. 5, we win. when we have this, the kindergarten numbers multiplied, that would be 36. X squared times x squared, you add the exponents. I should have really not even put that problem in there, because if you multiply 2 times 2 and add 2 plus 2, you get the same answer by accident. So that sometimes is why kids start to get the wrong idea. As they get the right answer, they think they did it right. Now we're going to multiply these. 6 times 4 is 24, the kindergarten numbers. We didn't make you learn all those things for no reason. 6 times 4, the kindergarten number part of these terms, still multiplies to 24. X cubed times x cubed, when you multiply, you add. We win. Here's another one. This stands for x cubed times xy squared. Check, we win. Now look. This time, I guess I better bring the whiteboard up here. Look how this is written. -2 to the 3rd squared. Now look, this 3 has the negative under its power. So that really means that this whole quantity is written down 3 times. So it's -2 times -2. Now you could make a mistake here and get the right answer in the back of the book, but it would be kind of tragic to get the right answer doing this thing wrong. So negative times negative times negative. Negative times negative is positive, times another negative would be negative. And these are kindergarten numbers, so 2 times 2 is 4, times 2 is 8. So this is -8 squared. Now, this negative is under the power of that 2, so this really means -8 times -8, which is positive 64. I guess I could slide this. Not that far. Like I said, I made this just to get some practice, like the kinds of problems that were in the remedial books. -2 squared, that's 2 negatives, that makes it positive, so this is 4. Check, we win. 24x to the 4th. I hope you get the idea. If, say we put something in that was completely wrong and we checked and say try again, and then there's help, it's going to give you some clues about what's true. So you might use that first program. When I started thinking about this topic, this is not what came to my mind. What I thought we needed was the laws of exponents. And I put my dog in here. After we do 10 problems, she's going to come out of the doghouse. So when we add terms that are alike, we can add the coefficients, but do nothing to the exponents. When we subtract the coefficients, do nothing to the exponent. We multiply, we add, we divide, we subtract, we raise a power to a power, we multiply the powers. You've got to try to get these things right. So let's try this. Here we're adding. The kindergarten numbers add, first of all, we need to make sure we have like terms. Now, I wrote this program, there are no adding problems where the terms are not like. I should have probably done that. But we have x squared y squareds added to x squared y squareds. They're the same kind of term, so we can add them. What happens to exponents when you add them? If they're like terms, nothing. So these both have to stay the same as they were. When you add x squared y squareds to x squared y squareds, you get x squared y squareds. Well, how many do you get? -5 plus 3, looks like the negatives win. You get -2. Check, we win. New problem. When we divide, we subtract. So -2 divided by 1 is the kindergarten numbers. That's -2. X cubed divided by x to the 5th. When you divide, you subtract. That would be -2. When you divide, you subtract. 1 minus 2, that would be -1. Check, we win. New problem. When you add, you do nothing. You can tell now that in this program there's not going to be an adding problem that you can't do. They are alike. When you add, you do nothing to the exponents. If we gave you one where they were different, you just would leave the whole problem alone. -2 plus 3 is 1. Check, we win. Raise a power to a power, multiply the power. This is 3 out here. Everything that lives inside that parentheses is under the power of this cubic. 1 gets cubed, but 1 times 1 times 1 is still 1. X cubed gets cubed. Raise a power to a power. This would be x to the 9th. Raise a power to a power, multiply the powers. This is y to the 3rd. Check, we win. New problem. Divide. -4 divided by 4 is -1. X to the 4th divided by x to the 1st. When you divide, you subtract. This would be 3. When you divide, you subtract. This would be -1. Check, we win. See how strange the rules. We haven't gotten any subtraction ones. Add. 4 plus 4 is 8. As it was in kindergarten, when you add, you do nothing. It stays x squared y to the 4th. Check, we win. Raise a power to a power. Now, 4 cubed, you might as well get used to it. It's a famous number in the higher math. They use it a lot on the AP. 4 times 4 is 16. You might not know, but 16 times another 4 is 64. So I'm going to scoot this all up to 64. Might as well memorize that while I'm doing that. 16 times 4 is 64. Raise a power to a power and multiply the powers. Check, we win. Divide. -3 divided by -3, the kindergarten numbers, is 1. Divide, subtract. Oh, this is going to be x to the 0 power. So it disappears, says anything to the 0 power is like another 1. Divide, we get -2. Check, we win. Hope you're getting the idea. We haven't gotten a multiply problem yet. Add. Oh, we got 0 this time. Because when you add -5 of these and +5 of those, that's 0 of them, and you don't need to put down the letters because 0 times anything is 0. Check, we win. Add. It's going to be 4. Exponents have to stay the same. Oh, there's my dog saying you're doing well. We still haven't gotten a multiply problem. Subtract. -3 minus 3 is -6. When you subtract, things stay the same. I knew that the laundry was going to go off, but I was pressing my luck. See you later. Bye.